Neural networks power everything. Voice assistants like Siri and Alexa, self-driving cars, and advanced medical diagnostics. But what are they really, and why are they so good at solving problems humans struggle with? By the end of this video, you'll understand what a neural network is, how it's built, how it learns, and why it's so powerful. A neural network is a computational model inspired by the way neurons in the human brain connect and communicate. In biology, neurons receive signals, process them, and send signals onward. Neural networks do something similar, but with math. At a high level, they're made up of layers of nodes, also called neurons. You start with an input layer, which receives the raw data. This could be pixel values from an image, audio wave patterns from speech, or numerical data from a spreadsheet. Then you have one or more hidden layers, where the real computation happens. Finally, you have the output layer, which produces the result, maybe the predicted label for an image, or the translated sentence in another language. Inside each neuron, the inputs are multiplied by weights, numbers that represent how important each input is, and then summed together. This sum is passed through something called an activation function, which decides how strongly that neuron should fire. The result is sent to the next layer, and the process continues until you get the output. This entire setup is what gives neural networks their ability to process and transform information. So why should you care? Neural networks are excellent at recognizing patterns in complex, messy, and nonlinear data where simple formulas fail. They can find subtle relationships and structures that would take humans an impossible amount of time to discover manually. Facial recognition in photos, real-time speech transcription, detecting fraudulent credit card transactions, or translating entire paragraphs between languages. There are no clear-cut rules for these tasks, but neural networks handle them every day, often with accuracy that surpasses human performance. This is why they've become the backbone of modern AI. But how do neural networks learn? It comes down to adjusting those weights we talked about earlier so that the network's predictions get closer to the correct answers. When you train a network, you start with random weights and feed in your training data, say thousands of labeled images. The network makes predictions and you compare them to the actual correct answers. This difference between prediction and reality is called the error. Backpropagation is the process of sending this error backward through the network to figure out how each weight contributed to the mistake. It uses a mathematical method called gradient descent to adjust the weights just a little bit in the right direction, reducing the error step by step. You can think of it like tuning a radio dial. You make small adjustments, check the signal, and keep tweaking until you get the clearest reception. Over thousands or millions of iterations, the network becomes better and better at mapping inputs to correct outputs. There's a proven concept called the universal approximation theorem. It says that even a relatively simple feed-forward neural network with just one hidden layer can approximate any continuous function given enough neurons and the right weights. This is a big deal. It means that, in theory, a neural network can represent almost any relationship between inputs and outputs, whether recognizing handwritten digits or predicting stock market trends. And this is the secret to their power. No matter how complex the pattern, there's a configuration of weights and activations that can model it. But not all neural networks are the same. The simplest form is the feed-forward network, where data moves in one direction from input to output without looping back. This is the foundation of all neural nets. Then there are convolutional neural networks, or CNNs, which are designed for image processing. They use convolutional layers to automatically detect features like edges, textures, and shapes. Another popular type is the recurrent neural network, or RNN, which is built for sequences. RNNs have loops that let them remember information from earlier steps, which is great for time series data, speech recognition, and language modeling. But the frustrating thing about neural networks is that they work incredibly well, but we don't always know exactly why. They're often described as a black box because while we can track inputs, outputs, and the overall learning process, the exact patterns they latch onto inside the hidden layers can be hard to interpret. This doesn't mean they're unreliable, far from it. In fact, they're one of the most consistent tools in AI, but explainability is an active area of research, especially in applications where understanding the why is as important as getting the right answer. And there you have it. Thanks for hanging out till the end, and if you didn't hate this, a sub would be awesome, and let me know your thoughts in the comments.